as usual, every time when we discuss a reaction, we're looking at the reaction mechanism. So for the nucleophilic isosubstitution reaction, the first step is when your nucleophile attacks on the carbonyl carbon. Under that circumstances, you're generating a tetrahedral reaction intermediate, okay? And I wanted to apologize that what I've written is really not looking like a tetrahedral, simply because it's easier to write, okay? Really, your reaction intermediate is tetrahedral. Once you're generating the tetrahedral reaction intermediate, and if your leaving group is good enough, the lone pair on the oxygen can be shifted back and removing the leaving group, essentially generating this substituted product. The reaction is generally referred to as containing an addition and an elimination in the reaction mechanism. Generally speaking, if we are looking at a generally energy diagram, we can write the potential energy as y-axis and reaction progress as the x-axis. Okay, so many of the nucleophilic isosubstitution reaction start with a reactants and going through a high energy transition state, generating a reaction intermediate, followed by a lower energy barrier and essentially generating the product. So under these circumstances, by looking at this energy diagram, the first mechanistic step is the rate determining step, and the energy between your reactants and your transition state, your first transition state, is the activation energy. Okay. The reaction mechanism we just discussed is typically referred to as a reaction mechanism under a basic condition. Okay, your nucleophile attacks on the carbonyl carbon in the first step, and with the corresponding energy diagram. If the reaction is carried out under a acidic condition, what's typically happening is you're going to first protonate the oxygen, generating this reaction intermediate. This reaction intermediate has a very polar carbon-oxygen bond, indicates in these two resonance structure. Under that circumstances, your nucleophile, even if your nucleophile is not a very strong nucleophile, notice I particularly didn't even write that negative charge for this nucleophile, and even though it's not strong, it still could attack on the partially positive charged carbon, generating a tetrahedral reaction intermediate, and lone pair from the oxygen can be shifted down after removing the leaving group, generating this reaction intermediate. Okay, so under these circumstances, whenever you have a hydrogen bonded to a positive charged oxygen, that hydrogen is very acidic. So this hydrogen is very much easily removed and essentially generating this substitution product. The reactivity of this kind of reaction followed the order of acid halide, anhydride, ester, amide, and a carboxylate or carboxylic acid, depends on what's your starting material. Okay, and the reactivity with this order is due to a number of reasons. Many of the books like to discuss the nucleophilic isosubstitution reaction, looking at the stability of the starting material, the leaving group stability, and the nucleophilicity of your nucleophile. Okay, so we're going to go over some of these together. And first of all, a lot of people like to look at the leaving group stability. Okay, and when we look at the leaving group and with the corresponding functional group, I listed the leaving group over here. You can see that the leaving group stability decreases from left all the way to right. Okay, many people trying to rationalize the reactivity of different acid derivatives based on the leaving group stability. To me, I am more interested in looking at the rate determining step. Earlier we talked about the first mechanistic step is the rate determining step, typically, right? So when we are looking at rate determining step and to determine how fast or a reactivity of a reaction, we wanted to focusing on the reaction intermediate and the reactants, right? And also the transition state. But we know that based on Hammond's postulate, the transition state is structurally resembles the reaction intermediate, and therefore if we are focusing on looking at either stability of reaction intermediate or the stability of the reactants, we can get better understanding about reactivity. Okay, so in this case, the stability of the starting material, the acids or acid derivatives, plays very important role in determining the reactivity. Okay. This is a handout page that posted in the handout package and for this chapter. And this handout in particularly compares the bond length of various bonds. Okay. And let's start with the acid chloride, which has a sp2 hybrid carbon-chlorine bond with a bond length of 1.79. In comparison, the sp3 hybrid carbon-chlorine bond has a bond length of 1.78 angstrom. There's not a whole lot of difference between the two bond lengths. Okay, and underneath on the very bottom, we have another comparison of sp3 hybrid carbon-fluorine bond and sp2 hybrid carbon-fluorine bond, again with similar bond length. Okay, and these two examples suggest that the carbon-fluorine or carbon-chlorine bond are very much a single bond over here. Okay, and what does that really mean? It could be understandable once we are looking at the example of an ester and an amide. Let's look at ester first. Okay, so when you have a sp2 hybrid carbon-oxygen bond and a bond length is 1.36 angstrom, in comparison, a sp3 hybrid carbon-oxygen bond has a bond length of 1.42 angstrom. You can see a difference, quite a difference of the bond length over here. And the reason there is a difference of the bond length is because an ester, we all know, is not really only look like this. An ester really is a resonance hybrid of multiple structures, okay, and very important contributor. I wrote another very important contributor over here. So as you can see that because your ester is a resonance hybrid, and this carbon-oxygen bond actually has a lot of double bond character and makes this carbon-oxygen bond much shorter than this carbon-oxygen bond. Okay. In the other word, ester is a lot more stabilized in comparison to an acid halide because it's stabilized by resonance. Similarly, when we look at the case of amide, in comparison to the case of amine, sp3 hybrid carbon-nitrogen bond has 1.47 angstrom bond length, and it's longer than the sp3 hybrid carbon-oxygen bond. Okay, because bond length decrease from left to right on the periodic table, so bond length is always longer for carbon-nitrogen bond compared to the carbon-oxygen bond. However, when we look at the sp2 hybrid carbon-nitrogen bond in the amide, and the bond length decrease even more drastically, okay, from 1.47 all the way to 1.36, and simply because that the amide, again, is a resonance hybrid of a number of resonance structures. And one of the very important contributor is written over here. And as you can see, there are more carbon-nitrogen double bond character for the resonance hybrid. In other words, because nitrogen is less electronegative And this particular resonance structure contributes more to the resonance hybrid for the amide in comparison to how much this resonance structure contribute to the overall resonance hybrid in the case of ester. In the other word, and the resonance hybrid for amide would have more carbon-nitrogen double bond character, and therefore the carbon-nitrogen bond is much shorter than this carbon-nitrogen bond. Okay, and this bond length also help us to realize that in the case of amide, the molecule itself is really very stable, have very low ground state energy because of the resonance. Okay, so the ground state stability decrease from acid halide to anhydride, which I didn't have a data here, followed by ester, followed by amide. Okay, and that can also help us to explain the reactivity of the acid derivatives for the nucleophilic azo substitution reactions. Therefore, the essential reason for the different reactivity really has to do with what we just discussed. The double bond character of the carbon-oxygen bond decrease from left to right. I should show you this list of reactivity as well, right? And because of that, the ground state energy also indicates that the ground state energy also decrease from left to right, from acid halide to amide. And because of that, the ground state stability increased from left to right, and the activation energy increase from left to right. Okay, in this rate determining step, when your ground state energy of the starting material decrease, the activation energy increase, and the reaction slows down. Okay. So once we know the different reactivity, we could take advantage of that to use the more reactive acid derivative to prepare the less reactive acid derivative. So for instance, we could prepare almost all the functional groups with acid halide, and then we could prepare these functional groups with anhydride, and on and on. Okay, and it's harder to prepare the more reactive acid halide from the less reactive acid halide with the nucleophilic azo substitution reaction.